Hello. Let's solve this system of equations, x squared plus y squared equals 4, and y equals x squared minus 1, using Newton's method. Now, obviously, this one has a straightforward algebraic solve. You don't need to use Newton's method, but we'll do it just because we can visualize it nicely and kind of see what's going on. So I have written the system of equations as a vector here. So x1 stands for x, x2, or x of 2 if you like, stands for y. I'm squaring both of these and then subtracting 4 because in Newton's method we move everything over to one side. And down here I've got this, so here I've got to subtract x squared to the left-hand side, so I'd have a negative x squared there, which looks like in Matlab, negative x1 squared, then plus x2, that's y, and then plus 1 because we're subtracting 1 on the right. So I want to find when both of those things are equal to 0. And to do that, I have to use the gradient of this function if I want to use Newton's method. But that's pretty straightforward to compute. So we just take the x derivative of the first component, and that just leaves 2 times x1. We take the y derivative, and that's 2 times x2, or 2 times y. And then the x derivative of the second component here just gives us negative 2x, or negative 2x1 if you like. And then the y derivative here, that's just the coefficient in front of this y term, which is 1. So I've called one of them f and one of them df. I guess you could call it gf for gradient. I just think about it as some type of derivative. I'm also using MATLAB's symbolic notation here. So if I, this is a notation for symbolic functions, and let me just show you a little bit about how that works. Let's say we had something like g is equal to, and I want some function of, let's do a function of x and y. Here we're just having a function of x, but let's say I wanted a function of x, y, I could put in a z or a t or whatever you like. And if we do something like x squared plus y squared minus 4, then later I can, so MATLAB creates this function, this symbolic function, and I can put in something like g of 2 comma 3, and we can check that, indeed, right, 2 squared plus 3 squared minus 4 is 9. So this is a nice way to deal with a function in MATLAB. You don't always want to use symbolic functions. Sometimes they can run a little bit slower. But when we're just doing a quick reference to things and we kind of want to write them down in a convenient way and we're not too concerned with speed, symbolic functions are a fine way to go. Notice here I've separated the columns of the matrix with commas, and I've got semicolons here separating the rows. This dot, dot, dot is necessary for continuation. Now, I could have put this all in one line, something like this, but to me, that's a bit harder to read. So I've written it in this way. Also, I kind of like it when I line up variables a little bit. It just kind of visually helps me to see what's going on a little bit. So you can do that if you like. All right, so for Newton's method, we're going to iterate this operation, and we'll start with some type of a seed. So let's say we start with x is equal to, and if you want, you could call it something like x0 is equal to, let's start at 5, 5 for the iteration seed, just choosing this to be somewhat arbitrary. And then we're going to have a for loop. So for, let's say k is equal to 1 up to, well, we have to decide how long we're iterating this. We could also use a while loop here and check when the error got down below a certain level. But just to make it kind of straightforward, I'll use a for loop. So in that case, I have to code in max iters, like the maximum number of iterations that I want here. So here I'll set max iters equal to, let's say 10. I'll put it toward the top so it's a little bit easier to find. I think in general for Newton's method, the convergence is so fast that probably using a for loop isn't exactly the best approach, because you might converge after, maybe 2 or 3 iterations, maybe 5 or 6 iterations. But again, I'm just kind of doing something for simplicity here. So you can try it with a while loop if you want. And then after that, it's not too bad. So we just take our x and replace it by x minus, And then it's going to be this matrix evaluated at x. No, sorry. So I need to say set x equal to this x0. So it might seem a little bit funny that I'm writing it this way. X0 is equal to 5, 5. I mean, I could just say x is equal to 5, 5, and then not worry about this x0. That'd be perfectly all right. But if you, say, converted this into a function where you were passing in a seed, it might be kind of nice to pass in a seed x0 and then store it as x. Anyway, a lot of different ways to do it. This is just a demonstration. So, but although notice that I have to have a semicolon here, I want to be passing in a column vector for this, for everything to work properly. So now I can just have df of x. So this is my derivative matrix, and then times f of x. And that should do it. This will give the Newton iteration. But, oh, sorry, except for one thing, of course, we need an inverse here. So the inverse, you could do it like this, I and v parentheses of that matrix. So this will compute the inverse matrix and then multiply it by the vector f of x. But this is usually pretty inefficient because what you're doing is computing, I mean, in this case, it's just a 2 by 2 matrix, so it's not really a big deal, but we want to write this in a way that we can scale to very large systems. Yeah, in MATLAB, even here, helpfully gives us this this warning. It says, hey, inverse of a times b can be slower and less accurate than a backslash b. So MATLAB has some built-in operation of using a backslash, which computes exactly that. It solves the linear system ax equals b without explicitly computing the inverse of a, typically much faster. Now, we've studied other versions of this. MATLAB with the backslash looks through several different solvers and picks what it finds to be the best one. So it's a little bit of a kind of quick and dirty way to do it. But I'll show you in a little bit a way we can do it with one of the solvers we've written earlier. All right, so we have this this iteration, and then we're done. We just plug this thing in. Let's see what we get if we just run it. Of course, I got nothing because I didn't ask it to put anything out. So I can ask it to display x, and let's see how that goes. And if I'm being lazy, I could just write an x with no semicolon, and it will spit that out. Okay, so we get an answer here. All right, well, is this a reasonable answer? We can, of course, check this algebraically and then plug it in and see if we believe that that's the case. But of course, a lot of times we don't really have a good way to check this algebraically. That's kind of why we're using a Newton method, right? So let's see if we can at least visualize this a little bit, which again, we can't always do, but let's just kind of, for the sake of our own understanding, let's try to iterate this a little bit. So I'll do it in the following way. So let's capture, maybe we'll do something like x all, and then I'll capture that x at each stage. So this colon here means I'm just going to allow for anything in the column vector range, and then this counter will count up 1, 2, 3, 4, and so on. But I'm actually going to want to initialize this. Of course, you could do this a little more efficiently by just using the xall vector itself and not worrying about the Newton iteration piece. That is, you could put xalls on each of these guys. But for now, I'll just say xall is zeros, and then it's going to be 2 rows by max iter's columns. But we'll actually notice what happens. We actually miss the first time through. So let's compute one of these in advance, say the first one. Then we'll get an xall equals x. So this will store the initial seed in the first column, and then each subsequent column will show up after that. But notice that k here starts at 1, so we could either start k at 2, or I could do something like k plus 1, but then I would need max iters minus 1 if I don't want it to go beyond that number of iterations. Okay, so this should now, each column should store one of our iteration vectors, and we can visualize this. So if I put something like, say, plot, and then, let's see, I had sort of a nice way to do this. Plot, let's see, it'll be x all, and then I want the x component of those at every time. So now I'm putting a 1 in the first column because I want the first row, and then any column. So this strips out the first row, and then the same thing. So the y variable is 2, colon, and this should plot those different iterations. But in order to see this a little bit better, let's say use a dash star, or we'll see in a later version of the code, I use a k dash star to make it black. This is a line in between each point, and then each point has a star on it. And I like it to put, I like to put here line width 2, just to see the plot a little bit better. And we see we get this kind of fast zooming in. It turns out this is the first point. There's that 5, 5, and then it's zooming in. And if you zoom in quite a bit here, you can see that we're converging to something rather quickly, right? There's actually several of those stars kind of right on top of each other. So we're getting this very, very fast convergence that we saw in the analysis of this equation. Okay, but you might say, okay, well, is it converging to the right solution? So I'll fast forward a little bit and show you kind of a finished version of this code. Although, let me switch to this. So here I've got the same start of the code, but I've also added in a plot here, which is going to plot the circle that we wanted to see. So I've just plotted the upper and lower halves of the circle here to define some, so if I do linspace -2 to 2, that gives me 100 points from -2 to 2. If I wanted 1,000 points, I would put in something like that. And I've plotted each of these with some various colors, and then bring the axis in tight so it's a little bit nice to see. And then I plot those iterations here like we were just doing. So if we run this, oh, and then I've also plotted, so I assume that the final solution is converged to something good, something close to the exact solution. And when we exit the loop here, x is going to be, oh, sorry, there we go. X is going to be just that, just the variable that we were hoping it would be. Excuse me, yeah, it'll be something just close to the exact solution. So I'll assume that that is the exact solution, more or less, and find these, you know, the norm of that vector. So we can actually view the error, and I'm plotting it in a semi-log plot. So if we take a look, here's what we see. So on the left, we have that parabola. This is the y equals x squared minus 1. We've also got the circle, a radius 2. And here's that Newton's method coming in, just zooming in very, very quickly down to this, this intersection. So it looks like we're getting the right solution there. You also see the error. Remember, this is a log-log plot. So if it was converging exponentially fast, like very, very fast, it would be a straight line on a log-log plot. But it's actually converging faster than that. This is that quadratic convergence where you're squaring every time. The error every step is getting squared. So we have this insanely fast convergence down to roughly machine precision in 7 steps. And you might say, well, why is it not showing more than that? Well, because the error at that stage is essentially 0. And so the log of 0 is undefined, and MATLAB's not showing those undefined points. It's getting an answer, not a number of points. We can change this a little bit if we take a different point, like minus 5, 5, for instance, different seed. Then we see it zooming down from the other side. And you can do other variations on this, like take something inside. And so, oh, I put a comma, so it didn't like that. We need a column vector. So this is something coming from the inside. It overshoots a little bit, but then very rapidly converges. You can also try pushing outside. So if you get something down here, if your initial seed is down here somewhere, you get this basically non-convergence, right? And the error is all over the place. And that's just showing you, if you're too far away from the 0, you might not get any convergence whatsoever. But for a wide range of points, it comes out pretty well. Here's another example. If you have 0, 0, you might say, well, that's a kind of nice neutral starting point. But then notice your matrix will be 0, 0, 0, 1. So that matrix is singular, and you get, MATLAB says, I can't perform this operation because the matrix is singular. So that's just, yet another thing to watch out for. Now, I wanted to finish with a different take on this. So if we don't want to use MATLAB's sort of internal black box matrix solver, we could use our own conjugate gradient solver. So for this operation, what I've done is I've just said, okay, I want to compute, AX equals B, with A being my Jacobian matrix, the DF matrix, and B, the right-hand side of the linear equation, being F. And if I do it, so I'm kind of maybe giving a little bit away here, but if I do it with a standard, say, conjugate gradient method, here's the matrix I'm plugging in. Here's the right-hand side vector. Remember, f of x is not a function. Once I plug x into f, I have a vector, right? So I'm not plugging in functions here. I'm plugging in vectors and matrices. Once they're evaluated at x, they are just numerical objects. I'm plugging in also a starting value. That's the seed of this of the conjugate gradient iteration. Now, I could see the conjugate gradient with something else, but x seems like a pretty reasonable choice. And then I have some max iters on this. Now, max iters for a conjugate gradient could potentially be different. Maybe I would put in 100 or something like that. But actually, maybe we'll just stick with the max iters from the Newton's method. The conjugate gradient takes often a lot longer to converge than the Newton method, but either way, I don't necessarily have to have perfect convergence here either. There's a whole subject on that. If I decide I want to solve this solve this equation imperfectly, like maybe I don't update this matrix every time, for instance, because it can be kind of expensive to compute the derivative matrix each time, especially for very large systems. Maybe I, use a secant method instead of a tangent method for computing this, or maybe some kind of hybrid version of those. So there's a whole subject on that called nonlinear optimization, which at UNL is a course labeled Math 433 or 833. We also need a tolerance here. So I've built in a tolerance here. So I want to go down to machine precision on that, which might not happen by the time I reach max iterations, but whatever. So I'll just store the answer to this question as inverse. I called it inverse of df on f. So df acting on f. Maybe I should use a lowercase there. And then we just subtract that off from f. So let's take a look at how this goes. And it doesn't like something. Yeah, it says, okay, so we've got doesn't like line 16. correct dimensions for matrix multiplication. I didn't expect that. Sometimes it can be good, I think, for you guys to see me work out a problem. So we've got a nice matrix there. What's f of x? It's a nice matrix. What's x? Same problem again. All right, it's a row vector, not a column vector. So let's try that again. Still doesn't like it. Is that from before? Oh, I see. I think I had something there with the breakpoints. Breakpoints should be cleared. There we go. Okay, so take a look at this. It's terrible, right? The error is up to 3.8 times 10 to the 17. That's positive 17, not negative 17. This picture is zooming all over the place. What went wrong? Well, the thing to remember is that conjugate gradient only works, if you have a symmetric positive definite matrix, or at least we know it works in that case. And so we don't have a symmetric positive definite matrix. So let's take a look at this, and I'll just sort of write it here in comments. If I want to solve ax, a different x, right, but just kind of a generic x, if I want to solve ax equals b, well, if a is not symmetric positive definite, it's not really legitimate to use the conjugate gradient. However, if I just multiply both sides by a transpose, a transpose, well, this is a legitimate operation to use in, if a is invertible, for instance. I'm not gaining or losing information here. Oh, that should have been an x there. Let's say times x. But then look, this matrix, so long as x, this matrix, A transpose A, is going to be symmetric positive definite, so long as A is invertible. So all of a sudden, I have the same problem, but it's it's just a little bit. We're actually getting some kind of positive definite quality out of this. So let's try this. So transpose in Matlab is just prime. Technically, that's conjugate transpose. If you want to do the real transpose, it'd be dot prime. So it won't conjugate your variables, but here our variables are real, so we don't care. So I've got to put it in there for the matrix, and then I put it in for the vector. That's this piece, A transpose times F. So the idea is that now the matrix I'm passing in is positive definite. Let's see how this turns out. Sure enough, we get very, very fast convergence happening once again. Not quite sure what this little blip is, but it's down around machine precision, so I think that's all we're seeing. And yeah, just screaming down super fast to the correct solution. So I encourage you to try this, write it in higher dimensions for a challenge. If you would like to write it in arbitrary dimension, go ahead, give it a try. And yeah, I think that's a good place to stop. We'll see you next time.